Hello ATS 113 students, this is Dr. John Schrage and I'm here today to talk to you about weather forecasting. Today we're going to learn not so much about how to actually make a forecast, but rather how television meteorologists and National Weather Service officers and the military makes forecasts of the weather, which then we'd also talk about how these forecasts are distributed and what they're used for and so on. Broadly, we're going to say that there's going to be two main types of forecasts that are issued each day. There's going to be the kind of forecasts that are made by people, and there are the kind of forecasts that are made by computers. The kind of forecasts that are made by computers, we're going to use the term numerical weather prediction, or NWP, to describe them. But let's talk first about the kind of forecasts that people make. Now think about all the kinds of things that we've learned about in this class, things like all the different kind of cloud processes and radiation and conduction and all the different types of clouds and all the different processes of cyclogenesis and cyclolysis and so on. You can well imagine that it's pretty much impossible for an individual to keep track of all of that stuff. As a consequence, these techniques that I've labeled as ways that people make forecasts are pretty simplistic. They're going to be just very, very basic kinds of forecasts. And the first one we're going to talk about is climatology. When you make a climatology forecast, what you are saying is the weather is just going to do what the weather normally does at this time of year. So for example, if the normal high on November 15th in Omaha is 52 degrees, you're going to say that the forecast is going to be that the high is 52 degrees. Is this much of a forecast? No, of course not. But it's a lot better than nothing. And so if you had no other data, this wouldn't necessarily be the worst way to make a forecast. On the other hand, a slightly more skillful way to make a forecast by hand is to make a persistence forecast. Now, persistence forecasting is saying whatever the weather is doing now, it's going to continue doing that. For example, if the high yesterday in Omaha was 60 degrees, you're going to say that tomorrow's high is going to be 60 degrees. Or if it didn't rain yesterday in Omaha, your prediction is that it won't rain tomorrow. Now, this again is not a terribly sophisticated type of forecast. On the other hand, it does represent the reality, which is that in general, once you're in an air mass, the temperatures are going to be fairly constant. The types of weather that you're going to experience are going to be fairly constant. And it's only when a front comes through and a new air mass comes through that there'll be significant changes to the weather. So persistence is not a terrible way to make a forecast. A somewhat more sophisticated technique that individuals can use to make forecasts is what we call trend forecasting. Trend forecasting says however the weather is changing, it's going to continue to change. For example, if the high 2 days ago in Omaha was 60 and the high yesterday was 65, you're going to say that tomorrow you think the temperature is going to be 70. It warmed up 5 degrees the last few days, it'll warm up another 5 degrees. Again, this is not a terribly complex way of making a forecast, but it represents the idea that once you're in an air mass and the air mass is modifying, it's going to continue to modify. If this cool, dry air mass is modifying and becoming warmer as it sits over Omaha, it will continue to modify. The fourth type of technique that we're going to say that people can use is quite a bit more complex. This is called analog forecasting. The word analog can be kind of confusing because you get it confused in your head with the idea of digital versus analog. But this is something different. Think analog as in analogy. You or a computer goes through enormous amounts of data looking at past weather patterns, and you look for weather patterns that are analogous or very similar to the current weather pattern. So for example, if you look at the current weather pattern and there's a trough in the western United States and a ridge in the eastern United States and a cold front in the Ohio Valley or something like that, either the forecaster or a computer goes through lots and lots of data and lots of past weather patterns, and they decide, hey, these days look just like today. And then they go and look through and see what happened after that. And then your forecast is just, you're saying that the atmosphere will do what it's done in the past. Now this takes an enormous amount of data. It usually requires a computer's assistance to make this kind of forecast. This kind of forecast is typically not made for like day-to-day weather. Rather, they tend to make this kind of forecast for like seasons. They look at patterns of El Nino, they look at patterns of sea surface temperature, they look at patterns in the jet stream, and they issue a forecast. What will this spring be like? Or what will the next 30 days be like, and so on. That tends to be what you use an analog forecast for. The more detailed forecasts that you see day to day on television, on the Weather Channel, on the internet, are numerical weather predictions. They are forecasts made by computers. And when you think about the large number of things we learn in this class, it makes perfectly good sense that there would only computers could keep track of all of these things. Many of the most powerful computers in the world are used in numerical weather prediction. This is actually a large Cray computer in this picture. These are actually quite out of date, but it reminds me of an old computer I saw on a tour. And these computers are used by running what we call computer models of the weather. Now let's talk about models for a moment in a more generic sense. Here's a model of an airplane made out of Legos. It's a pretty simple model. Is this an airplane? No. But in some ways, this one, are a lot like airplanes. They have a lot of the same characteristics a real airplane would have. They have wings. In this case, this one has a windshield. It has landing gear. It has a tail. On the other hand, here's an even more complicated model. This model is a better representation of what a plane looks like. For example, this plane has a propeller. And this plane has lights. And this plane sits on a tricycle gear the way a real airplane does. So this is a better model. You could learn more about a real airplane by looking at this model than you could at the previous one. And we could make progressively more and more complicated models that still aren't real airplanes. If we threw this, it would not fly. But you could learn a lot about real airplanes by looking at these Lego models of these airplanes. The more sophisticated your model is, the better a representation it is of the real system, in this case a real airplane, but it is still not a real airplane. The same way then, we're going to have computer models of the atmosphere. And these computer models are not the atmosphere, but they are computer programs that act a great deal like the real atmosphere. These models are not made of Legos. They're made of computer code. Thousands and thousands of lines of computer programs that reproduce the behavior of the real atmosphere. This computer program is not the atmosphere. It is a model. But it is a model that reproduces many of the behaviors of the real atmosphere by carrying out the actions of the 7 primitive equations. Okay, so let's talk for a few minutes then about these business of these 7 primitive equations. Models work by applying the 7 primitive equations to observations of the atmosphere. And what are these equations? Now, I know that when you hear the term equation, you start getting chest pains, and you should, because these equations are really horrible. They're long, they have lots of terms, they involve calculus, but we're not actually going to worry about the equations themselves. We're going to say, what do these equations mean? Now, 3 of the 7 primitive equations are pretty straightforward. They involve something that we learned in this course, forces. So these terms of the 7 primitive equations are going to involve things like the pressure gradient force, the Coriolis force, the centrifugal force, friction, gravity, the kind of processes that contributed and forces that contributed to things like geostrophic balance, or the gradient, we didn't learn gradient cyclostrophic balance, and so on. The way forces lead to wind are the first 3 equations of the 7 primitive equations. Equation 4 of the 7 primitive equations is the ideal gas law. We learned the ideal gas law. This is definitely the simplest of the 7 primitive equations. We actually learned it. P equals rho RT. It relates pressure, temperature, and density to each other. The fifth law in this, the 5th equation in the 7 primitive equations is the first law of thermodynamics. Again, that's a real mouthful of a name for an equation, and it is a messy, long set of equations, and it's a very complicated process, but it involves relatively straightforward ideas that we've already learned in this class. Shortwave and long-wave radiation, conduction, advection of heat, things like that. Processes that change the temperature of air are described in terms of the first law of thermodynamics. Our 6th equation is called continuity. Now, this is a fancy word for something that's not really